Hi, my name is Kristóf Umann. I'm a university student at Eötvös University, and I've been working in Ericsson on the Clang Static Analyzer for just shy of 2 years. And today I'm going to talk about bug report construction in the Clang Static Analyzer. Now, why is this the penultimate challenge? Well, the ultimate challenge of static analysis is, of course, the analysis itself, namely finding bugs. But I don't think I have to emphasize the importance of clear and precise bug reports or error reports, because they are oftentimes one of the main bottlenecks of development. It was also one of the main selling points of Clang back in the day against GCC. And the issues that GCC faced back in the day, at least in my understanding, wasn't down to poor wording. Since by the time we discovered some sort of an error, so much information was lost that it was difficult to come up with a good error message. So let's talk about how the analyzer deals with this issue with another layer of complexity. First, I'm going to talk about how path-sensitive analysis works in the Clang Static Analyzer. Then I'm going to talk about how the results of this analysis are later turned into bug reports. At last, I'm going to talk about the still remaining challenges that we are facing today. So the talk just before mine, given by Artyom Delgachev, was more detailed about how path-sensitive analysis works, but bear with me as I'm going through this. So the Clang Static Analyzer is a very powerful tool to analyze the C family of languages, and it can find tools and it can find bugs and code smells in the code, and it employs a variety of techniques. For example, matching the abstract syntax tree, or AST, just like Clang Tidy does. It implements analysis on the control flow graph, or the CFG, for example, to find that code. But the focal point of this talk is going to be all about symbolic execution, which is the most complex and powerful of them all. So, you can imagine symbolic execution as some sort of a simulation of the code. So what it will do is it will take the control flow graph of a function, and it will explore paths of execution on it. Whenever it encounters a branch in the control flow graph, it will explore a path of execution on which the condition of that branch is true and one on which the condition of that branch is false. Now, one of the most immediate questions that arises from this is that how does this work interprocedurally? Because, of course, a control flow graph is always built for a specific function. Well, it is solved with a technique that we like to call inlining, and I'm going to talk about that in just a minute. I'm going to show you this code snippet plenty of times during my talk, so allow me to walk you through it on this first occasion. We can see in function main that we are initializing a variable x to a null pointer, and you are setting the global flag variable to true. Then we are calling function foo, where we will reset flag's value to a value that we do not know, as we do not know the value, do not know the body of coin. After the function call, depending on flag's value on line 12, we may or may not end up initializing x. And after that, on line 14, we are calling foo again. We are resetting flag's value again. And after the function call on line 16, depending on flag's value, we may or may not end up dereferencing x. Now, there is already, we can see that there is a bug to be found here, namely that if on line 12, flag's value is false, and on line 16, flag's value is true, we will dereference x as a null pointer. So let's see how the analyzer will find this specific bug. So it will start in the control flow graph of function main, and it will jump from the entry block to block 4, where it will note that flag's value is true and x is a null pointer. After seeing the function call to foo, it will jump from main's control flow graph to foo's control flow graph. And this is the process that we like to call inlining. So in some sense, you could say that the algorithm still works intraprocedurally, but within another function. Symbolic execution continues in foo. It will note that flag's value changes to an unknown value right here. It will go back to function main after the inlining ends. And if flag's value is false in this case, it will go to block 2, where we can see the analyzer noted flag's value here. We will inline foo again, we will reset flex value again, and after that, if flex value is true in this case, we will jump to block 1, where we can see that x is still believed to be a new pointer, yet we are dereferencing it. Okay, so this was one path of execution, but the analyzer explores multiple of them. And in order to keep track of all of this information, it builds its own custom data structure called the ExplodedGraph. And the ExplodedGraph contains all paths of execution, all values of all variables in every single program state that it explored. So let's see from a bird's eye view how the building of this ExplodedGraph works as the analyzer explores this program. So on the left-hand side, we can see how the analyzer goes through the control flow graph and how the ExplodedGraph is built on the right-hand side accordingly. I will show you much enlarged versions of the graph very soon. After the analysis concluded, we are left with this graph. Now, obviously, I am not doing static analysis any justice here because it's a lot more complex. For example, branches in the ExplodedGraph do not necessarily correlate to a branch in the control flow graph. For example, in the case of loops. And also, I mentioned the name Symbolic Execution, yet I didn't explain what symbols really are and how values are represented by the analyzer. But there is a lot more to talk about that, and you can maybe check out Artyom's talk on that. And of course, exploded graphs are very, very large, and what I've shown you was a gross simplification of it. Now, with that being said, this is just about enough to talk about how the results of this analysis are later turned into bug reports. After the analysis is concluded, we are left with this exploded graph that may contain several error nodes or bug nodes. And these are the points at which the analyzer discovered some sort of an error. And the goal of bug report construction is to explain the path that leads from the root of the exploded graph to these error nodes. So in the first step, the analyzer will construct these so-called backpaths that will lead from the root to these error nodes. It will construct the shortest path there. If we take a little closer look at this exploded graph, we can see the backpath is right here. And if we extract this backpath, as the analyzer would do, we are left with this short backpath. And I like to think that this backpath really captures the essence of this bug. We can see how flex value changed during the analysis. We can see how axis value remained unchanged all the way to the point where it was dereferenced as a new pointer. So what are we shooting for here? What is an ideal bug report? Well, we would like to create a bug report that contains every information that is relevant to the bug, but minimal in the sense that it doesn't contain much else. In order to achieve this, we have two techniques. We are using the bug reporter visitor infrastructure to achieve completeness, and we are using interestingness propagation to minimize the bug reports. It's worth noting here that the analyzer processes the backpath in reverse. So from the arrow node to the root of the exploded graph, visiting each node individually, and may or may not deciding to create a diagnostic message for it. Let's talk about bug reporter visitors then. So for any given bug report, a variety of them can be registered, and what they are doing is that their visit node callback method is called whenever the analyzer visits a new node, at which point these visitors may decide to create some sort of a diagnostic message for that node, and that's basically what they are doing. Now it's worth mentioning here that the name bug reporter visitor is a little misleading, because these should rather be called bug reporter callbacks, because they do not visit the backpath individually. But this is something that we have from the past, and we just decided to deal with it for now. Let me give you a couple of concrete examples. Condition bug reporter visitor is a visitor that if it finds a condition in a exploded node, it will describe something related to that, for example, conditions of if branches, or loops, or conditional operators, etc. Find last or bug reporter visitor is not as general of a tool. It may be registered a number of times to always describe a specific variable. And the goal of this visitor is to find the last store to this variable. And since the backpath is linear and it contains every information that the analyzer gathered so far, it makes this visitor's job trivial in terms of arguing about data dependencies. And in order to complement this data dependency analysis, we also have a visitor for control dependency analysis. Now, admittedly, I have a little soft spot in my heart for this visitor because this was my Google Summer of Code project, which was mentored by Artyom Delgachev, Gábor Horváth, and Ádám Balog. And what this visitor will do is that it will calculate control dependencies to certain points of interest. And it will ask the analyzer to better explain control flow around these points of interest. So let's see a concrete example. We can see here that the point at which we discovered the bug was in block 1. And we can calculate that block 2 is a control dependency of block 1, because depending on flag's value, control may flow in this direction or in this direction, which implies that the value of flag in block 2 is very meaningful for this bug report. So this visitor will tell the analyzer to explain its value better. Let's talk about then about interestingness propagation. So during analysis, a variety of variables or symbols will be marked as interesting. And during bug report construction, entities that interact with these variables or with these entities will be marked interesting as well. And in order to use this to minimize a bug report, we can discard diagnostic messages that do not describe an interesting entity. We can combine these two, bug reporter visitors and interestingness, to achieve expression value tracking. So whenever I say that we are tracking X, what we really mean is that we are marking X as interesting. We are registering a variety of visitors to explain X's value a little better. And it's also worth noting here that this is the thing that the control dependency visitor will do. So it will tell the analyzer to track flag. OK, so this was the dry stuff forward. Let's see how this works in action. I already alluded to the fact that this backpath is a gross underrepresentation of its true size. And this is a little closer to reality. What I did here is that I split up the first function call into 4 separate nodes, as I did with the second function call, and I split up the final node into 2 separate nodes where first we assume flag's value to be true, and one where we dereference X. OK, bug report construction works in stages. The first of which is going to be the collection of visitor nodes. So we are working from the bottom up. The checker that emitted this error already started tracking X. Moving one node up, we will find a condition that condition bug reporter visitor will describe, namely that we assume flag's value to be true. Within that same node, control dependency visitor will see that this node is associated with a control flow block that is a control dependency of a point of interest, namely the error node. So it will tell the analyzer to track flag. Moving a little further up, we will find the last store to flag. So find last store visitor will construct the diagnostic message here. And moving even further up, we will find another condition where condition bug reporter visitor will create a diagnostic message again. We will find another store to flag, but we already found the last store to flag, so we are not doing anything here. And all the way in the root of the exploded graph, root of the backpath, we will find the last store to X. Now, after this is done, we are collecting in the second stage all the auxiliary nodes. For example, the retrieval of the warning message from the checker, describing events such as returning from a function, entering a function, or calling a function. And the same thing happens here as well. After this stage is concluded, we are basically done with diagnostics construction. So now we will use interestingness to prune parts of it away. And if you take a look at the first function call, it doesn't really describe anything interesting. So, so we can prune that away. And after this point, we are basically done with the bug report construction. The analyzer will emit some sort of a file to describe this bug report that can be used by graphical interfaces to display a human readable format like this. And this is displayed by Code Checker, which is also an open source tool maintained by Ericsson. And I think it really shows what the analyzer thought in order to reach this conclusion here. Now, it's worth noting that our already existing infrastructure, the bug reporter visitors, could be used for a variety of other things. It's also worth noting that we could write always more visitors. We could write individual visitors for individual checkers. We could always use different kinds of interestingness. So there is a lot more to be done in that department. But this is something that we already have the infrastructure for. So this is a great time to celebrate because there is absolutely nothing to be done at this point, right? Well, unfortunately, no. And as I said in the beginning of my talk, the issue that GCC faced, or at least the way I know it, the issue that it faced was a lacking infrastructure. And this is the same issue that we are here dealing with today. So let's see well, what are those. So first, what is very difficult is whenever there is a problem, there's a point of interest that is outside of the bug path, we have very little tools to find those. In extreme cases, for example, like an inline assembly call, it may also happen that we end the symbolic execution prematurely, leading to an information not even being found in the entirety of the exploded graph. So let's take a second look at this bug report, because I said that it's pretty good, but it's nowhere near perfect. So you can see that in the second condition, how we do a very good job at explaining why flex value is the one that we believe it to be. But if we take a look at the first condition on line 12, it's not explained very well. And especially only looking at function main, it's not immediately obvious why we believe flex value to be possibly false. Because mind you that we just initialized it a couple lines up. So a naive approach would be to just always explain these conditions better. But the problem is that these conditions may not always be meaningful, which would go against minimality. So unfortunately, I do not have any foolproof way to solve this problem. We have had a lot of discussions on it. For example, we could explore the entirety of the exploded graph rather than just the back path. But that has its own pitfalls. So for this talk, I'm going to focus on only one approach that we took, which is called reaching definitions analysis. Now, reaching definitions analysis describes an algorithm where we calculate the last stores or definitions to a variable. And our idea was here to regard all of these reaching definitions as a point of interest. And we have already put a lot of effort into implementing it. Let's see a concrete example. So we can see that in block 1, we found the error. And the source of this error is variable x. Now, we can see that on this path of execution, the reaching definition to x is its initialization to a new pointer. But on this path, we can see that the reaching definition to x is some sort of a dynamically allocated memory region. So what we could do here is to tell the analyzer that block 3 is a point of interest, which would trigger much of the already existing infrastructure to explain control flow around that point. Unfortunately, however, there are plenty of pitfalls to be found here as well, namely that this algorithm wasn't really implemented, or wasn't really thought out for C and C++. And it's very difficult to nail what a definition of a variable is. Think of like losing sight of a void pointer, which was passed to a function as a non-const reference. It may point to any variable in that function, at which point we have to invalidate everything. It doesn't argue about pointees, aliasing, and we again face the problem of this algorithm being only defined for the control flow graph. And although we have some ideas as to how we could turn this into an interprocedural algorithm, with the use of the information that we already have from bug reporter visitors, there is nothing concrete here just yet. So, what are the key takeaways from this talk? We established that clear and precise bug reports are very important. It doesn't really matter how good our analysis is and how many bugs we can find if we do not communicate those well to the user. At the end of the day, a living and breathing human who has a great knowledge of the code base will have to take a look at all of our results. We talked about, in a nutshell, how the analyzer works. And we talked about how the results of this analysis are later turned into bug reports with the use of bug reporter visitors and interestingness propagation. We also talked about, in our still remaining challenges, that in order to argue outside of the bug path, we have big difficulties in doing that. And we oftentimes think about we have to basically re-implement symbolic execution to do it properly. With that being said, I can confidently say that the analyzer is really getting better by the minute. There are a lot of very talented people and very passionate people working on it. We always have more students and more students coming into the scene. And also, it's worth mentioning that some of the things I talked about leaned on the works of George Karpenkov from last year's talk. Also, Artyom Dagachev is working on making the bug reporter visitor infrastructure even more user-friendly. And as a final note, this is the bug report that we would have emitted before the summer. And what is worth noting here is that the analyzer didn't even realize how meaningful flex value is in the second condition. And by implementing control dependency analysis, we were at least able to realize how meaningful flag is in the second condition. So here's one slide from my sponsors who funded parts of my travel here, as well as the LLVM Foundation. And that basically concludes my talk. So if you have any questions, maybe suggestions, ideas as to how we could approach these problems, I am all ears. Thank you.
We have time for some questions.
So I think the control dependency work is really exciting. What do you think is the next low-hanging fruit that we should try to tackle in the analyzer community to make bug reporters better?
I have a couple immediate ideas. So the low-hanging fruits, so we have a lot of checkers that are still in the alpha stage. And we do not enable them by default because they do not have their own bug reporter visitors. They do a very poor job of explaining how they reached the conclusion to find the bug. And what would be a very low-hanging fruit is to write individual visitors for these checkers and finally be able to enable them by default. I can't confidently say that reaching definitions is a low-hanging fruit, though we have made very good progress with it, so maybe that, I guess.
More questions? I have a question. For when we generate bug reports, right, in a large code base, we might have a ton of bug reports.
Mm-hmm.
And when the software evolves, then the bug might be the same, but now it may think that this bug is a different bug. There are some measures in Clang Static Analyzer currently, but do you have any insight that if it can be improved even further?
So the thing that you are talking about here is that how we unique out these bug reports. Is that correct?
Yes.
How we could improve on that. So This was an idea we fetched during my summer of code. So the immediate question is I have no idea. The longer answer is I have a couple ideas. The first one is, so if we try to argue outside of the bug path, one of the most immediate ideas is to not discard the rest of the exploded graph. And by using the entire exploded graph, we might be able to realize that some bug reports are similar to another. That would imply us having to prove that one path of execution is similar to another. We have no clues as to how to do that. Another idea, I guess maybe just that.
Thank you. Yeah, thank you for your talk. Very helpful. More questions?
So very important consideration is when a developer makes incremental change, and I'm just wondering, this graph and reports, are they able to report interesting information or relevant information just related to the new change that developer made?
Mm-hmm.
Compared to the previous errors in the code?
So suppose that you write a new checker and you are interested in that whether the existing infrastructure is able to explain that.
No, the particular question is, let's say I'm a developer and I change just one code in my source code base.
Oh yeah, I see. So not the analyzer, but the code base.
How this reporting will be impacted, and do you see difference between reporting as if the code is for the beginning, or you just reporting the particular root cause?
So if I understand correctly, whether if you make a small change in the code base, whether the bug report only shows relevant changes to that little change. No, I think that you would get a whole new bug report for that. If I think that's the answer. No.
So do you feel the need of reporting just things that are relevant to your change to make incremental progress?
It would be great. I shamefully admit that I have absolutely no ideas as to how we could do that. Yeah.
See if the backpath includes your most recent code change, then those reports would be interesting to you, right? That would be an initial idea of how to isolate.
I mean, sure, it's a possible approach to just do the work that is supposed to be done by the analyzer and take a closer look at the bug report that is only relevant to your change. But other than that, I absolutely have no idea.
I just have another comment on this topic. So when you analyze your code, you may happen to have a lot of initial errors. And then when you do your change, then actually you may have, let's say, one new different bug report. But then actually there are tools with which you can create a difference to the previous state. And for example, one such tool is the code checker he was talking about. Actually, you can store the results of the analysis in a database, and then you can see the differences of each and every analysis run. I don't know if that answers your question. Code checker, yes.
It does do a poor job of displaying the differences in between the same bug reports. So. Yeah, I don't think I have any idea for a toolset that could do that just yet.
Just to make sure, those reports are also in the procedural, right?
Correct, yes.
Analysis is procedural, reports are based on same procedural cross-file analysis, right?
So you have a question about whether the challenges that we face with cross-translation unit analysis, is that right?
So analysis is cross files. Reports are also cross files, right?
I think if you enable cross-translation into analysis, that is correct. You would get a bug report that is all going through multiple files. Is that correct? Yeah.
More questions?
Yeah, so in Artem's talk, he showed off scan build, and you're obviously talking about code checker. Like a recommendation of which is a better approach for someone's start essay? Is code checker going to be committed to trunk, or how? What do you recommend?
I am aware of. So code checker is developed by Ericsson, and scan build is a part of the LLVM library. Now, which one I would recommend? I have very little experience with scan build, so maybe I'm employed by Ericsson, so I'm biased. But I do think it's a very great tool. So it's like a very amazing interface over the Clang Static Analyzer, and we plan on. It can also drive Clang Tidy, and maybe we are thinking about adding more, like support for more analysis engines as well. So I think it's a very great tool. I can't honestly compare it to scan build. It's a great
But we have to use your branch to use code checker as the main trunk, right? Or is it committed to trunk?
It's not committed to the trunk. We have had a pull request or a patch that would have added code checker to the main Clang, to the main tree, but we decided to abandon it, and I joined the project recently, so that's been before that, so I don't have any comments on that, unfortunately.
Thanks.
So hi, I'm actually a code checker developer. So the thing is that code checker can use any version of Clang. So whether that's an upstream Clang or our own fork, which supports C2 more better than what we support on upstream Clang. It's just a matter of configuration. So code checker provides you this graphical interface and the database, so you can have a difference of the runs. Okay.
Any more questions? All right, let's thank our speaker.